So we start the next topic in our course today, fluid kinematics, and these are the three concepts that I plan to cover. And hopefully today I can go through velocity and acceleration, and then in the next two lectures I'll try to focus on Reynolds transport theorem. Again, what has worked for me so far in this course is in the first two modules, especially module 2 and 3, statics and dynamics. I kept it very light on concepts and put more examples, which is what we'll continue to do. So right now, even though these words are all new to you, we'll quickly try to see what these are and focus on examples. Okay, keep doing more of it. Before I do that, I just wanted some quick polling about how was the exam last week on Tuesday? Was it difficult, easy? Yeah. Okay. Can you be more specific? Okay. Okay. Make sure you write that in the course feedback. Thank you. Yeah. What else? Any suggestion? Was it too easy? Was it kind of going with the lectures? You feel like you learn? Are you learning something new? Yeah. Okay, if you have any adverse feedback and you don't want to tell now, you can email me or tell me in person. You want to say something? Okay. Okay. So thank you. I hope everybody is happy and learning. We want to talk about the next topic in this survey of fluid mechanics called kinematics. You've heard this word before. Can you tell me what do you understand by kinematics? Equations. Just the word. When you say something is kinematic, what does kinematics mean? Why should we call this all these headings? Put a topic name called kinematics. Can we give some other name for this? Sorry, it pertains to fluid motion. It's a synonym. It's not an exact match, but it describes fluid motion. And when you talk about fluid motion, what's the most fundamental aspect? So far, we have discussed about how a fluid is made of molecules which are in constant motion. And when something is flowing, they are collectively having a velocity directed in a direction and they go towards that. And let's say you think of an example like a sphere, like a tennis ball, and the flow of air around a tennis ball. What's the most defining attribute of fluid motion? Or what quantity should you be tracking in order to say something is moving or is in motion? Velocity. Velocity, right? So when we talk about any point, there are the shorthand version is at that point there are many molecules. Okay, and if the local velocity is in pointed that way or some direction, all these molecules are having that velocity, and they are also having some random component due to their thermal motion. But as a collective, they are all going in that direction. That's why we call the fluid is moving or in motion with a certain local velocity. So this local velocity here, V, what you need to understand is the velocity of the fluid can and most often will vary with spatial position and time. We'll talk about this statement, but what you should first write down is the velocity of the fluid is not a single number at every point in space. It will vary with space and time, and how we describe that is really pertaining to what we call as velocity field. So if I write the velocity, I give it a symbol v vector. Obviously, velocity is a vector. And this velocity depends or varies from point to point. So I'll call this v at point 1 and v at point 2, v at point 3, and so on. I can keep representing these. And every point may be assigned a position vector, okay, and we'll say this position vector R is described in terms of the XYZ coordinates. So we'll say this velocity depends on the position vector. So it depends on position. Depends on position. That is part of the statement is velocity of the fluid will most often vary with spatial position. That's what I've written. And it can also change with time. And we'll talk about that, but I'm just going to write it can be a function of both position and time. This quantity, we call it velocity field. Why add the word field? We're just talking about a single velocity at a point, it's just one quantity. But since we are talking about the velocity varying from point to point over a field of values, we say it as velocity field. Okay? This velocity field is a function of r and time or t. Okay? And as you know, velocity is a vector. Since velocity is a vector, we can express v of r comma t is equal to, I'll call the x component u of r comma t I cap plus v of r comma t j cap plus w of r comma t a cap. What are u, v and w without the vector symbol? I mean, you know vector algebra, right? So what do you call the three numbers that together make up a vector? There's a name for it, you know that. You said directions, what was it? Unit vectors. These are unit vectors. The I, J and K are unit vectors. What are the numbers that go along with the unit vector? Scalars, right? Scalar. They are scalars, but I mean, okay, the name is important because first of all, they are called components. Okay, they are essentially the proportion along each direction. In components, essentially say when you have a vector, when you write it with a certain as a certain velocity, you can resolve it into different directions, and these are called components. Okay, so u, v, w are the components. They themselves are scalars, and they can be positions of space and time themselves. Are functions of position and time as well. You have all taken dynamics, right? Right? When you in dynamics, you learned about velocity and you learned about acceleration. When you learned about velocity in dynamics course and also acceleration, whose velocity was that? When you say velocity, or when you have, let's say, a little particle flying with a certain velocity, It's the velocity of a particle. And that is given as v equals the rate of change of position. Does it ring a bell? You've seen this, right? And when we talk about acceleration of the particle, of the same particle, a is the rate of change of velocity. It's like a baseball that's flying around. If you track its position in over time, you can compute its velocity, you can compute its acceleration. Okay, so the classic definition is velocity is rate of change of position and acceleration is rate of change of velocity. I just wanted to refresh this. Okay. Now come to this context of fluid flow. Okay. Let's think of something. Okay. Let's say we have a funnel like for your project and a stem, and you fill this with some very heavy liquid like glycerin, which is very viscous. That's my point. It's very viscous. And let's say you have a bottle of a liter of glycerin ready with you that you keep refilling this. For our discussion, we'll assume that the flow of glycerin from this funnel is constant. It's just constantly, steadily dripping at a constant flow rate. Okay, so steady drip of a highly viscous liquid. It's steady. Nothing is changing. Nothing changes with time. And then I'm going to keep like a sphere, like a tennis ball, and let the fluid wash this ball and drip out. I'm trying to establish a flow which doesn't change with time. Steady flow of a thick viscous liquid over a tennis ball, such that if you just take a movie of this, it will look as though there is no flow. Everything looks steady and static. Okay, so this is an example of what is called as a steady flow. Okay, if you take any point in this flow field, if you take any point in this flow field, and if you just try to monitor the velocity at that point, the velocity at any particular point B, let's say we take this velocity, it will look steady over time. So if I calculate partial V over partial T, this is equal to 0. Are you with me so far? I'm creating a steady flow. I'm asking you to pay attention to what happens at this single point. And let's say it could also be done by sticking some kind of a velocity probe in there and reading out what the probe will be outputting. And that flow is so steady that, contrary to my diagram, it's a steady constant velocity. Okay, at this point, velocity is not changing. So what is the acceleration of the fluid at that point?
There's no acceleration, 0.
Acceleration is 0. Okay, that is, you're saying if you just focus your attention on that one point, the velocity at that point is not changing with time, meaning the acceleration and I should write it elsewhere. Meaning the acceleration at that point is 0. With me so far? Yeah, okay. And how do I denote that I'm worried about the acceleration at a point and not at any point? If this point has a position vector of r, I will say the velocity or the time derivative at r equal to r naught, let's say this is r naught, equal to 0. The local velocity change with time is 0, or the local acceleration at that point is 0. With me, Christina? Good? Legion? Good? Okay, so now tell me, do we expect the velocity of the fluid at, let's say, this point, we'll call it P1, and another point, we'll call it P2. Do we expect the velocity at P1 equal to the velocity at P2? Do we expect it? We don't expect it, right? The fluid is far away from the ball. It must have some velocity. As it comes closer, it has to turn around the object, and then it has to again kind of keep flowing. So I'm not asking you to compute anything. I'm just asking, will this velocity be same as this velocity? No. No. So in your sheet, just write your name and start putting down just the answers to these questions that I keep asking you. And after class, you have to upload it to Canvas so that I have a written proof that you are in class. Okay. All right. We don't expect the velocity at P1 to be equal to P2. So is the fluid accelerating between P1 and P2? Is the fluid accelerating? You just told me the acceleration at just any particular point is 0 because nothing is changing if you just focus your attention on this point. But if you focus your attention, zoom out, and you just focus on 2 points in the flow field, between those 2 points, there is a velocity change. So is the fluid accelerating? Yeah. Yes, we would think so, right? If there is a change in velocity, then we would think, yes, there is a change in velocity. There is a change in velocity. Right? So is the acceleration not 0 or non-zero? It has to be non-zero. There is a change. So first thing is we got to capture how to capture or calculate the acceleration of the fluid. Identify that there are two reasons by which fluid velocity may change, and one of them is due to change in velocity with time. That's the first case where you compute the partial derivative of v with respect to time at a given point. It is the change in velocity with time at a given point and number two, what is number two? Okay, I'm going to give you an example. How many of you have done rafting? Whitewater rafting. right? You've gone on a boat, you've gone down a rapid, and at some points you don't have to do any rowing. You just get into the right stream. The stream will carry you downstream. Correct? Am I describing it right?
Yeah.
So if you just get on the raft, let's say we draw an example. Let's say here is the rapid, and here you are on the boat. You are just going to go down here. Okay, so here, let's say you are drifting with a certain velocity, we'll call it V1. And when you get down here, your V2 is going to be greater than V1. Okay, listen, no need to write. Let's stop. Let's figure out this. You are accelerating just because you are going along a certain streamline and the velocity is changing from V1 to V2. You did nothing. You at that point or this point, you are not doing any work. Okay. So between these 2 points, can we say we accelerated? It's not about you. It's not about the boat or about your rowing. Whatever object you place here, it will pick up V1 and it will be carried downstream and reach V2. Okay. So the change in velocity. So let's say at time 1, you are here. At time 2, you are here. My goal is to ask what is the change in velocity over the time that we care about or which we are observing this. That would be V2 minus V1 divided by T2 minus T1. Okay? And I told you V1 or V2 has nothing to do with you. If you reach this location, we'll call it X1. And if you reach this location X2, X2, you will reach that velocity. Okay, so this change in velocity has nothing to do with something changing with time. It's mostly got to do something changing with position. So it's like writing. This is equal to the rate at which velocity changes with position multiplied by change in position. Right? At this point, you will have a V1. At this point, you'll have a V2. It's the rate of change of velocity with position multiplied by the change in position. And the change in position is not just happening by itself. It is happening over a certain period of time. This is what we call speed. If you move from point 1 to 2 at a certain time, that's what you call speed. So this is nothing but dv over dx multiplied by v. So the acceleration, what we think is always the rate in which speed changes, is here caused not by something changing over time, but something changing over position. Yeah,
I get what you're saying.
we'll put it in math.
Okay.
If you understand, if you just remember that rafting example, you start upstream, you sit on the boat, without you doing anything, the boat will take you somewhere where the velocity is V2. The river is basically you are at the mercy of the river. The river is at V1 and then the river is at V2, and that is purely because you went from position X1 to X2. If you go from X1 to X2, whether you are a boat or a little bird, you will be carried with that velocity. Me? Okay. So this type of acceleration, that is the first cause is if you just sit here, if you somehow hold yourself there, at that point, it will look like the velocity will never change if you're just localized at that point. But if you let yourself go from one point to the other, the velocity changes due to position, due to the flow field itself, and that causes the acceleration. So the first cause is local rate of change. The second cause is due to change in position in the flow field. If you let your fluid go from point A to B in the flow field, it will naturally accelerate or decelerate, and that's what is happening here. Imagine this, what will happen when a syrupy thick liquid flows around a tennis ball? It has to accelerate around the ball. It will come to rest at the center, but it has to turn and go around the object and then rejoin at the other side. So all this involves every direction change involves a change in velocity. Wouldn't you agree with me? Any change in direction involves a change in velocity. Okay. So this is purely because you are going through the space and we'll put these two together. Okay. So this here, this acceleration is the rate of change of velocity multiplied by velocity itself. I'm writing this in one dimension, acceleration in 1D. I'll write it in 3D shortly. So the acceleration total is equal to acceleration local plus acceleration spatial. A local is the rate of change of velocity at a point, that's why it's called local, hence local, and a local is equal to the rate of change of velocity at that point. A spatial is the rate of change of velocity due to fluid motion due to gradient in fluid velocity in the flow field. Okay, and right here, A spatial is equal to V dot del times V. I know that has a lot of vector calculus in it. I'll expand it for you. A spatial equal to the partial derivative of V with respect to X times V, sorry, the partial derivative of wait, hold on. So this is partial derivative of V with respect to X times U I cap plus partial derivative of V with respect to Y times V J cap plus partial derivative of V with respect to Z times W K cache. Where recall Q, V, W are the components of V. And we'll do examples. I don't want to just throw the formula at you. We'll do some illustrative examples. So the total acceleration is the partial derivative of V with respect to t at a given point plus local spatial. How do you make sense of this local and spatial? Like how to think about this? Okay, so I'm going to give you an analogy. How to think about local and spatial. Any initial thoughts? Yeah, not exactly. So I'll give you an example. This class is 18 students and me, so totally 19 people in this room. If I come here, let's say every Tuesday and Thursday between 11:20 and 12:45, and I pay attention to you only during that time. I'm worried about you only when you are in this room at this time. After 12:45, I really don't care where you until you show up the next time, hopefully. So the idea of being local is you should see it as local meaning it is focusing on a point in space, point or a volume in space, and tracking how the quantity, in this case velocity, changes with time. Simple example is I'm interested in what goes on in this room, whether 18 people show up or 16 people show up or whatever number of people show up. What they do during this time is what, or in this space, is my concern. Okay, that is local. That is, you are focused on a certain volume in space, like let's say this particular volume, and you just try to monitor whether the velocity in that space goes up and down or increases or decreases. It's only about what happens in that space over time. Okay, those who are writing, take a break. We will give time to write. Local meaning focus on a certain volume and see whether the velocity at that point goes up or goes down, and so on and so forth. Then how do you think about spatial? Same example, this classroom, this group of 18, if I want to understand you not when you are here, but in some other way, how would I do that? So this group of 18, when you are in this room, I take attendance, I monitor your attention, I see what you're doing, I monitor you, or I worry what happens to your behavior over time when you are here. If I want to do the same outside this space, or even not worried about this particular space, but wherever you go, if I want to track you, what should I do, or how would I think about it? Let's say I tag all 18 of you, give you a GPS device, you all go in different directions, but essentially I'm tracking you, tracking this 18 people wherever you go. That would be paying attention to your spatial motion without worrying about wherever you are. I'm tracking you, not okay. If I just worry about whoever comes into this volume. So today we have a guest here. Okay, I'm going to use you in my example. So we have somebody who is not part of this class, but he has come here, and since he is here, I would take note of that. I'm interested what goes on in this volume. If some of you don't show up, or some of you show up, or some new person shows up, I'm interested in what happens in this volume that is being local. I'm interested in this spatial location. But if I truly care only about the people taking this course, that those 18 students, and I want to know what they do in the rest of their time, I would track what they do or where they go and so on and so forth. That would be like we are one entity. We are 33-31 class of Springs 2026, and I'm tracking that group, which may not be always confined in this room. That point of view is called spatial. Spatial is focusing on a fluid particle. A particle is nothing but a word that just is a bunch of molecules. And how the quantity, which in this case is velocity, changes wherever the particle goes. That is, it's like a point of view camera where I'm tagging the fluid with a camera, and I'm just traveling with the fluid at the same velocity and see what kind of changes it experiences along that motion. So this is always, let's say, going like this. Imagine I'm like this boat. I just travel with the flow, going with the flow, and whatever I record along the way, I report it as a value. So I'm going to make you do another thought experiment. So we'll take that rafting example. Okay, so here you are at point 1, here you are at point 2. Let's assume the river is very steady flow. Okay, steady flow. So if you just put a velocity sensor at point 1 and record its output, how will it look like? Just
Be constant.
it'll be constant, right? The velocity output at point P1 will be constant over time. Do you see that? Yeah? Now, I'm going to let my velocity sensor float with the river. Just drop it in the river, but it still has a transmitter that it will still record the velocity and transmit it back to my computer. How will the output of that look like?
When the velocity is zero, just flowing with the river.
The river is flowing. Let's say it is a sensor that can measure the local velocity. When you previously just fixed it at point P1, it kept outputting constant value, not zero, constant value. Now the river is flowing and this sensor is going along with the river with the same velocity. What will it transmit back to you? The velocity will still be constant, right? So if this is the position, let's say this is x1, this is x2, okay? You know the river is accelerating, downstream. So this is x1, this is x2. Let's say the velocity of the river increases linear. So what will your transmitter output? Your transmitter as a function of time. I'm sitting in the bank with my computer waiting for the signal to come back. What will my recorder actually show?
It will increase.
It was as time increased in service velocity.
As time, let's say at T1, I am at x1, at the sensor is at x1. At T2, the sensor is at x2. So I would record the same thing that I record here. Right? Right? So if I ask the question, in this first picture, what is the acceleration? You would tell me the acceleration is 0 because it's steady flow. The velocity at point P1 is not changing. Right? Whereas in this case, you would say the acceleration is v of x2 minus v of x1 divided by t2 minus t1. Right? But you do know that this change in velocity is not due to time change. It's due to you going from here to here. And you are carried there at a certain speed. Okay? But this velocity change itself is not due to local change, but spatial change. So if you knew what is the rate at which velocity changes over space multiplied by the change in the position, you get a change in velocity. Does this look familiar from basic calculus? If you want to know what is the change in distance, you take the slope and multiply it by the change in x. Right? So this is exactly that. But that is not happening statically, that is happening dynamically. So you write this is equal to this is nothing but v. The rate at which you move from x1 to x2 is nothing but your speed, the fluid speed. So the acceleration is velocity multiplied by the rate at which velocity changes in space, and we have a term for it. This is called velocity gradient. And that is why we are able to now come to this statement that says A total is equal to the rate of change of velocity at a local point plus v times dv dx. The reason I had to go through this is because we are so used to thinking about this. This is what your particle acceleration is. You have a rigid body, you throw it, it just has a velocity and it continues with that forever. But a fluid particle is not a rigid body. It's a collection of molecules whose shape can change as you go. So this term here gets more complicated as the fluid particle distorts in shape. It won't remain as what it is over here. As it moves along, it will respond to the forces, change shape or deform, and it will get more complicated. It's like this. You are all here, 18 of you, as a group in this room. But the moment you step out, will you all be together? Of course not. You all go in your own groups or individual. And that fluid, if I call all of you a fluid particle, the shape of that particle or your relative positions will continue to change as you go out of the room until you come back here next time. So magically you come back here, your shape comes back to the original 18, but the moment you go out, you deform and you all go in different directions. Is that making sense? Yeah? Okay. That's just an analogy. All right. So that's a lot of theory. We are going to put this in action, do some problems. Are we ready? Any questions? Something not clear, something vague? You want to ask something? That face suggests something is not clear. You, yeah. Yeah. Okay. All right. Let's try this. Example 4.4 from the textbook. Okay, we'll start simple. Example 4.4 from the text. An incompressible, inviscid fluid flows steadily past a tennis ball of radius r. So we'll draw a sphere, and that sphere has a radius r. Okay, and we want to talk about the fluid flow around this fluid flow around this tennis ball. Okay, look up. I'm reading from the problem. According to advanced analysis of the flow, translation, don't ask me where this is coming from. I'm going to give you a velocity field and make you do this calculation. Okay, that advanced analysis is something we may touch upon later in the class, but for now, take my word, take the book's word, that the velocity field is given by V is equal to Q of x I cap, which is equal to V naught times 1 plus R cube over x squared, or sorry, R cube over x cube I cap, where V naught is a constant. Of course, it has to be. And V naught is a velocity, so the dimensions will make sense. So that's okay. Okay. So look at this function V naught. Firstly, it has only one non-zero component. Only x component is present. That is its velocity. It's like saying this vector has only velocity in the x direction. It has no other components. So that will make this a one-dimensional flow. If it has two non-zero components, that would make it a two-dimensional flow or three-dimensional flow, okay, by extension. Not only that, if you think of this object, let's say we'll define the center over here, 0, 0, 0, and this is the x-axis. So this is a sphere, which means this point is r, 0, 0, and this point on the other pole is minus r, 0, 0. Okay. if you consider the fluid velocity far away from the ball, what would it be? What would be the velocity of the ball far away? That is, if this is the x coordinate, I'm asking you to think about what if x, or if you take any point that is either on this side or far away on this side. That is, the value of x is much greater than r, which means x is much greater than r, or x is much less than minus r. According to this function, what will be the velocity at faraway points?
Times 1
Or v naught,
or b.
right? So this little function here, if you think x goes to infinity or x goes to minus infinity, r cube over x cube becomes 0, right? If you divide this r cube by a very large number, it will become small. So this, for this faraway point, the velocity approaches v naught I cap. What does that mean? It means far away from the ball, the velocity is just parallel to x-axis and flowing nice and steady. Okay? Even before you do any calculation, can you tell me, as the fluid approaches this ball, will it accelerate or decelerate? Will it speed up or slow down? Put that down on your sheet. Just the answer. Will it speed up or slow down as it comes towards the ball? From the left, it's coming towards the ball. Is it slowing down or speeding up? Don't look at the equation and think mathematically. Think intuitively. What will happen if you have a ball and a flow of air or some fluid over the ball? As it approaches the ball, will it slow down or speed up? It will slow down. So we have one answer. How many of you say the same thing, or how many of you have an alternate? Yeah. Same thing. Okay. What did you want to say?
There's that something.
Same thing. Anyone else wants to say something else? Yeah. Correct. X is approaching minus r. That is, I said don't think mathematically, but as you come closer, you are getting close to this minus r value. So you're saying it increases. Are you saying increases everywhere, or you're saying increases at any particular location? So yeah, let's talk about the axis. If this is your axis, this is minus r 0, 0. Along the axis, is the fluid accelerating or decelerating? We had 3 people say decelerating. You're saying accelerating? That's okay. You just say something. We'll start the discussion. Okay, along the center line, it is decelerating. And you don't need math to tell you that. You have fluid here and it's going towards a wall. Essentially, at this point, this looks like a little wall. It has to slow down. It has to come to rest at this point. Okay, but if you are a little bit away, or if you are kind of in between here, you not only slow down, but you also have to change direction and you go around here. So if you are not along the center line, you are going to undergo some acceleration, which leads to a change in direction and possibly some change in speed as well. And you are accelerating around the object. Okay, so of course, the lesson learned here is acceleration of the fluid is in general sensitive to position Along the center line, you might reach different conclusions, whereas away from the center line, there may be different conclusions. Okay, so now we are asking the question. Now we are asking the question, what is the acceleration of the fluid at any point which is defined by its x coordinate? The acceleration would be, as I always, this is the problem solving strategy. Acceleration at any point is equal to the local acceleration at that point plus the spatial acceleration at that point. At any point is the local acceleration at that point plus the spatial acceleration at that point. The local acceleration is you take the function and you differentiate it with respect to time at any point r naught, or at any point r naught, or the point we are interested in. That's what I mean. This is, in this case, the derivative of u of x I cap at any value of x, which is the derivative with respect to time. What is u of x I cap? V naught times 1 plus r cube over x cube at a particular value of x. How to evaluate this derivative with our math knowledge? What is V naught? Is it a constant or a variable? Does it change with time or does it not change with time?
Constant.
It's a constant. Okay. So we can write this is V naught times partial derivative with respect to time 1 plus r cube over x cube at a given value of x. R is a constant, radius of the ball. So we don't have to worry about differentiating R. And we just said we are interested in a particular value of x. So x also cannot vary with time. So this whole thing is 0. Local acceleration is 0. Why does that make sense? Sorry?
Zero, right?
Steady flow.
1 second, I need to silence my phone. But yeah, what are you saying?
Is it a steady flow?
Steady flow, just look at this function. This flow has no dependence on time. If you just take any particular value of x, nothing here depends on time. If suppose I had a term that looks something like this, let's say I had v naught times time divided by L or something. Let's say I had a function which had a time dependence, then there would be a local acceleration, or forget time. I would write this as, let's say I multiplied this with sine omega t I cap, where omega is some frequency at which the velocity goes up and down at any given point, like a wavy motion. Then this problem would have a local acceleration, but we don't have it here. So local acceleration is 0. I spoke so much just to establish 0. Okay, but okay, then how do we compute the spatial acceleration? A spatial would be the rate of change of velocity vector with respect to space multiplied by the x component I cap plus the rate of change of velocity with respect to y direction multiplied by the y component j cap plus the rate of change of velocity with respect to z direction multiplied by z component k cap.
The first one,
Louder please.
only the first one you're taking this section out.
There is no y component or z component given. So these two are zero off the bat. This is a one-dimensional flow. There is no y component, z component, so we can ignore them. Okay, so now see. So the A spatial would be the derivative with respect to x of u of x, which is v naught plus 1, sorry, times 1 plus r cube over x cube multiplied by the x component, which is again v naught times 1 plus r cube over x cube. So this is du over dx, and this is u. So du over dx would be minus 3 v naught r cube over x to the fourth. Yeah, x to the fourth multiplied by v naught times 1 plus r cube over x cube. This should be minus 3 v naught squared r cube divided by x to the fourth times 1 plus r over x cube. That looks ugly, right? That looks ugly, all right? But without doing any math, just by looking at the function, what all can you comment? What all would be trends that you can predict by looking at the equation? This one?
No.
No. This one? Okay, okay, I'll give you some pointers, okay? Let's evaluate. Let's evaluate what is the acceleration spatial when we are or when the or at points that are far away from the fluid, that are far away from the sphere. Meaning, I want you to try x much less than minus r or x goes to minus infinity. How will you evaluate this when x is very highly negative and much larger than r?
Did you forget the cube on the R, or did I miss a?
Yeah, I missed that. So when x is very large, we would write 1 plus r cube over x cube is almost same as 1. Would you agree with me?
Yeah.
Right? This is a large number, or this is a small number, so it's almost equal to 1. Okay? So we would write the acceleration in that case scales as minus 3 v naught squared times r cube divided by x to the fourth times 1. Just taking this expression and using it here. Okay? And x itself is going to be quite large. It's like going very far away from the sphere. So this whole thing approaches 0. Okay, before you jump into an Excel sheet and start doing the numbers, I just want you to see these trends. So what happens when x is much greater than r, or x goes to plus infinity? Can the same argument still apply? Right? Same thing still applies. It would still be 0. That is far away from the ball on either side, the acceleration goes to 0. That should make sense because far away from the ball, the velocity is constant, so the acceleration must be 0 if velocity is constant. Right? What happens at the surface? Think about at x equal to minus r. What happens?
One minus one.
If I take this a spatial and substitute x equal to minus r, that will be like writing minus 3v naught squared times r cube divided by minus r to the fourth multiplied by 1 minus r cube or 1 plus r cube divided by minus r the whole cube. What is this?
That's one. X is 0.
That is 0, right? You recognize this is 0. So a spatial goes to 0 at the surface of the ball as well. So it's 0 very far away to the left. It is also 0 at the surface. So if I were to plot this from, let's say this is minus r, okay, this is x goes to minus infinity. How would this graph look like? It would start at 0. Whatever it does in between, we don't know yet. It has to terminate at 0. You with me? It's 0 far away from the ball to the left. It is also 0 at the surface of the ball. Did you have a question? Did you have a question? Okay, what goes on in between? Should we draw the intermediate points like this? Should we draw it like this? Should we? It has to start at 0 and end at 0, or maybe it just stays 0 all along. How will you graph it? Will this function ever stay at 0? Will it rise up? Will it? What do you think will happen? Okay. I'm going to play with your calculus knowledge. Okay. If I draw the velocity profile like a triangle with a sharp turn and sharp change here, is it even physically possible? No, right? Why?
It needs to be like steady. Not
Maybe
explain.
continuous.
Continuous, yeah.
It is continuous. It's not differential, meaning at every point the slope should exist. You can't draw a velocity profile that abruptly changes. That's physically impossible. So if you draw this in the exam, this curve, I don't even have to think. The velocity cannot have a discontinuity in slope. So I have to, that's not correct. Probably this is correct, but how do we know that it reaches a peak or not? If I give you Excel, then that's the end of the story. You won't learn after that, you won't think after that. But how do you say whether it will reach a peak or not? Yeah. Louder, please. I'm not able to hear you.
If x is equal to r. that's
Okay.
right?
You mean over here? Well, means this function depends only on x, even though they say it's a sphere and everything, they have given us a one-dimensional problem. So even if you drew a graph that looks like this, all the arguments still apply because we are dealing only with one dimension. Okay, so my question to you is, it's the velocity is 0 far away. I'm sorry, the acceleration is 0 far away. The acceleration is also 0 at the surface when you're approaching from the left. At some point, it has to rise and then fall. How will you locate where it rises to the top? Calculus, come on.
Set the derivative equal to 0.
You set the derivative equal to 0. Thank you. So if you want to locate where it goes to a maximum, you take this function. If this is your acceleration of x, you take the derivative of the acceleration and set it to 0. That is this location. I mean, I'm asking you to think about it because you have to understand how this acceleration varies. When it reaches a peak, when it starts to fall, we need to be able to say that just from this function or just from this function. So how will we compute that? How will you locate the point or x value? How will you get the x value at which acceleration spatial, which depends on x, hits a peak? Now x is less than or equal to minus r. That's our assumption. So you have dA over dx equal to 0, or the derivative with respect to x of minus 3 v naught r cube over x to the 4, 1 plus r cube over x cube equal to 0. You can do this, right? That is calculating the derivative, setting it to 0 and solving for x. We'll do it. Okay, I'll show you how we will do it. 3 v naught r cube, are they relevant? They're not, they are constants, right? So in this calculation, we don't have to worry about them. So it's like writing the derivative of 1 over x to the 4th plus r cube plus 1 plus r cube over x cube equal to 0. How will you compute the derivative? You write derivative of two functions, uv, what is it equal to? The product of two functions is u times dv over dx plus v times du over dx. So apply that. Please do it on your sheet, which you can keep, but you'll have to upload a picture. So I'm trying to get the derivative of this. I'm going to continue here. This is minus 4 over x to the 5th, 1 plus r cube over x cube plus 1 over x to the 4th minus 3 r cube over x to the 4th equal to 0. Okay. So I'm going to drop off this x to the 4. So I have minus 4 over x, 1 plus r cube over x cube minus 3r cube over x to the, sorry, I have x to the 5th, x to the 8th here, sorry, yeah, x to the x cube, so this will be 3x cube equal to 0. So this is minus 4 minus 7r cube over x cube equal to 0, or this would be 7r cube over x cube equal to minus 4, or x equals minus 7 over 4 r 7 over 4 to the cube root times r. Okay, don't worry about the numbers. Look up, see this. What is 7 over r? Is it a number more than 1? Yeah? Yeah? 7/4 is more than 1. So cube root of a number more than 1 is also more than 1. And then I have a minus sign and r. Now what is the significance of the point where you have minus r? What is the significance of the point? That is the surface of the sphere. So I am talking about a point which is, I'll write this as x equals minus alpha times r, where alpha is slightly greater than 1. So that would be a number to the left of minus r. So this will be x equal to minus alpha r. I'm not worried about the exact number. All I want to know is the acceleration will hit a peak at a distance that is slightly ahead of the surface of the sphere. That would be this point. So I know the acceleration hits a peak here, and then it has to drop to 0. So I first predicted this, I then predicted this, then I predicted this. With just 3 points and some basic knowledge about calculus, I am able to draw a smooth curve that has to hit a peak and then go through here. This is intuition. This is how you should build your velocity profile. And after this, you can do your number crunching with Excel and compute the values at each point, but it will fit with your general understanding. Is this landing? Sorry to ask. Because if I just tell you, take an Excel sheet and plot everything, you won't learn anything. That's why I want you to first be able to sketch this out, and then you should fill the gaps with numbers. Questions? No questions because it's too clear. Okay, so here is one more question. If I ask you, where does the velocity hit a peak? The velocity is also, if you go far away from the ball, the velocity is 0. At the surface of the ball, also velocity is 0. Where will the velocity hit a peak? If you have to plot the velocity curve, will it attain the peak at the same value as the acceleration?
You said velocity is constant.
Velocity is constant over time, but it does change from point to point position. So where in space will the velocity hit a peak? That's the question. It has to start at 0, end at 0. Of course, it's not going to remain flat. It has to rise, reach a peak, then fall back to 0. I'm asking, where will it fall back? And is it at the same location where the acceleration hits a peak? Answer that second question for me. Will it attain a peak at the same point where the acceleration reaches a maximum?
No.
No, that's correct, I think.
If it's a peak after the acceleration peaks up curve.
Okay, you're making a prediction. Can we check that? Can we test it?
So what I'm thinking is if the acceleration is still in effect after its peak, the acceleration will still have an effect on the velocity, so the velocity will continue to increase.
Very nice. So you're saying if the acceleration hits a peak here, it is still accelerating, but a little bit slowly, which means velocity will continue to rise until it goes to zero. Okay, so now if you extend that, where will this acceleration be? So you're saying it's going to be between here and here. It has to be between here and here. Is the logic making sense to others?
I think it'll be when acceleration hits zero.
Yeah.
Once the acceleration hits zero, it'll.
That happens only at the surface of the ball. It happens at the very end. After that, we are not worried about what happens. We are just asking until that fluid reaches the surface, where does the acceleration peak and where will the velocity peak?
At that same point at the surface, or would it be just before the surface?
Okay, so you've made two predictions now. One is the velocity peak has to come between the surface and this point. And you're also saying the velocity will peak only at the surface.
No, it'd have to be before the surface.
Because at the surface it is zero.
Right.
It has to peak before the surface, right? Okay, so we can use the same approach. If you want to know where the velocity is peaking, what would you do? You would take the velocity and set it to zero. That would be d over dx of v naught 1 plus r cube over x cube equal to 0. This is minus 3r cube over x to the 4th equal to 0. Seems to be a problem. Seems like the only solution to this equation is not 0. X is infinite. The only way this equation can be true is when x is a very large number. Some mystery, huh? Okay, yeah.
Is the initial velocity the largest velocity? That's what
Interesting.
I'm saying.
So she is saying the peak already happened at the leftmost and it's all downhill from there. Right? That's what you're saying, correct? So you can check that easily by plotting velocity versus x. At x goes to minus infinity, at x goes to minus infinity, velocity is u naught or v naught. V naught. After that, it's all downhill and goes to 0. That's your prediction. Correct. Okay, so what I thought what you said was this function, the maximum value it can attain is v naught, and that happens when you are far away on the left. If you are anything other than infinity, with a negative sign, this function only can go down and reach 0, because the last value of x is minus r, for which this function is 0. I thought you said it starts here and only goes down, right? That would make sense, right? Yeah, very nice. So this understanding of looking at an equation and using some simple calculus to figure out where certain quantities will reach a peak. For the mathematician, it's all math, but for the engineer, you should be able to intuit from the equation. That's why being able to do this from the gut and not with Excel sheet is important. Okay, so we'll pick up more examples on at the next lecture. So there are 2 more lectures I plan to spend on this topic. We'll keep it light on examples. There is one more concept I have to teach and then along the way some examples. Okay, thank you.